All right, we are recording. We are now in section 10.2. And wow, I bet you were wondering, when are we going to get to some derivatives and integrals in this course, right? Well, we're there now. We're learning about vector functions. We saw some vector functions in section 10.1. And now we're going to look at the process of taking derivatives and integrals of vector functions. So first off, calculus of vector functions, that's what we're learning here. So here, and I'll deactivate I don't want any email interrupting us here, so let me take that off. Okay, so how many of you does this kind of remind you of something, this definition for the derivative of a vector function R? It looks, how many is this? Is this sort of, this is kind of familiar, this definition of a derivative in section 10.2. Simon, it's familiar to Simon and Arian. Yeah, and you know, what you're used to, I mean, if we want to, you know, go back and back through time a little bit here, back when you were in calculus 1. Yeah, well, remember, that's right, Mary. So so when you wanted the derivative of a function at a value x, you would take the difference between the function at x and at x plus h, divide that by h, and let h go to 0. And this would give you the slope of the tangent line to some function at the value x. Okay, that's what that would do. So that was the formal definition of a derivative that you learned back in calculus 1. But now we're dealing with vector functions, and the vector function definition is very similar. It's just, instead of taking, you know, you're taking the difference of two vectors in the numerator and dividing by h. So one vector is evaluated at t plus h, the other vector is evaluated at t. So the difference quotient is a vector, because the difference of two vectors on the numerator is a vector, and you divide it by h, you're still going to get a vector, and you're going to get a tangent vector. And what does that look like? Well, let's take a look here. Let's take a look at a picture. So figure 1 is the secant vector. So if you take the difference of the vectors evaluated at t plus h and t, okay, and take that difference and divide by h, I want to be a little bit careful here. Well, let me just one moment here. So in the picture, they're calling the secant vector, well, yeah, that's exactly what it is, right? We remember from calculus 1, secant line. So what do? In calculus 1, when we learned about the slope of the tangent line to a point on a curve, we had the point, you know, of interest, and then we had another point, and we brought that point on the curve closer to our point and studied the slope of the secant lines that connected the points, right? And the slope of the secant lines turned out to approach the slope of the tangent line. Okay. In other words, I'm not saying this right. The secant lines were the lines that connected 2 points on the curve. As the secant lines, as the 1 point on the curve moved to the other point, the secant lines approached the tangent line, right? So in this case, in figure 1, we have a secant vector. Well, if that as Q approaches point P, the secant vector is going to it's going to approach that red tangent vector that you see in figure 1b. Okay, that's what it's going to approach. Now, the derivative vector we divide by h, right? We have to divide the secant vector by h. But I mean, does it make sense what you're seeing in figure 1? A and B. Does this make sense? Sometimes it just helps to look at it. What that figure is illustrating is the idea of the derivative vector. So the derivative vector in figure 1, that red vector in figure 1b, points in it. So again, if you think of the secant lines, the secant vectors, as h gets smaller, the secant vector PQ, as h gets smaller, Q will approach P. So the secant vectors are going to eventually point in the same direction as the tangent vector to P. But of course, the derivative vector is the limit of the secant vectors divided by h as h goes to 0, and that's what you're seeing in part B. Give me a thumbs up if this makes sense. These figure 1, A and B. I think the geometry is important. All right, Alexander's feeling it. Christopher, Narina, Yeva, Logan, wonderful, wonderful. Ara, Abdullah, are excellent. Abdullah, excellent. Alberto. I mean, are there any questions at all? Wonderful. IB's good. Simon's good. Okay. Okay. Well, then, how do you think you would find the derivative vector? How would you compute it? Well, the way you would find it is you would take the derivative vector, the components of the derivative vector are just the derivatives of the parametric equations that form the components of your derivative vector. It's really quite easy to see this. Now they have a nice little proof below. Let me just, so maybe maybe I can just, if I can have it fit. Yeah, I think that'll work. I think it will. Yeah, so r prime of t is, you've seen that, so instead of using h approaching 0, they're having delta t approach 0. And they just use the properties of vectors and bring in that scalar delta t in the numerator into the components, which you can do. You know, scalars can be moved out in front of the, the components of the vector or into the components of the vector. And then you end up with 3 limits that turned out all to be derivatives of the components. I mean, really quite amazing, I must say. And so that proves that shows that it's quite easy to get a derivative vector. Okay, and remember, a derivative vector is a tangent vector to the space curve at some point P on the space curve. So in the first example here, they say, okay, find a unit tangent vector. Okay, so sometimes you want your tangent vector to have length 1. Well, first you have to find the derivative vector of your space curve, and then you have to normalize it. So what they do in this example 1 is they have r of t is equal to 1 plus t cubed I plus t times e to the negative tj plus sine of 2tk. So to find the derivative vector, you just take the derivatives of each of those components, and obviously you're going to be using the product rule to get the derivative of t times e to the negative t, that second component. And the third component, the derivative of the sine of t, you're going to use the chain rule. So now you get r prime of t. But on part B, they say, okay, well, when t equals 0, find the unit tangent vector at that point where t equals 0. Well, so what you have to do there, it's quite simple really, is r of 0 is, hold on, I want to say this the right way. Yeah, if you substitute in t equals 0 in the derivative vector above, r prime of t, you will get the vector j plus 2k. So the tangent vector then is just the r prime of 0 divided by the length of r prime of 0. And so that gets you your tangent vector. And the tangent vector is 1 over square root of 5 times the vector j plus 2 over square root of 5 times the vector k. It's that simple, really. Are there any questions on example 1? Okay. Okay, well then let's move on here. Example 2, they have a space curve. It's a planar curve because there's just components I and j. So they want you to, for r of t equals square root of ti plus 2 minus tj, find the vector function and sketch the position vector and the tangent vector at t equals 1. Okay, so of course, you find the derivative vector and evaluate that vector at 1. And so r prime of 1 is 1/2 I minus j. But what's r of 1 equal to? If you put t equals 1 in the space curve, what do you get for your coordinates? Let's see, hold on here. So when I say the space curve, I'm talking r of t. R of t. Not the derivative of the space curve, but just if you were to put t equals 1, look below example 2 for the curve r of t. Okay, Alberto, that's right. When you put in t equals 1, you're going to get the coordinate 1, 1. So that means on the space curve, at the point 1, 1, that's when t equals 1, the tangent vector ought to be equal to 1/2 I minus j, which is r prime of 1. And that's very clear from the picture. So they say here in figure 2, we draw the position vector, okay, r of 1, starting at the origin, and then the tangent vector, r prime of 1, starting at the point 1, 1. Where would the tangent vector be useful in physics, by the way? What's the tangent vector represent in physics? Does anybody know offhand? Let's say you have a car that's moving along that path in figure 2, that blue path there, okay, a car. And let's see here. Well, I want to be a little bit careful here. I tend to like taking like a ball and swinging it around on a string. Let's say you're taking a ball and you're swinging it around on a string, and the path that the ball's taking is that blue path there. And after 1 second, you release the ball, and it's going to go right along that r prime of 1 tangent vector. R prime of 1, well, Sadhana, it isn't acceleration, but it's velocity. So Sadhana, you were close, and excellent credit for trying. And in fact, Logan and Narina, Logan says velocity, and that's right. And Narina's saying actually it's instantaneous velocity at time equals 1. That's exactly right. It's a velocity vector. It's a velocity vector. Okay. So that's something we're going to learn. We're going to see on Thursday's class, but just a little precursor. So we can do, if we want to find the tangent line to a space curve, three-dimensional space curve. Okay, so here you want to find the tangent line to the helix with these parametric equations. Now, these parametric equations, this helix in example 3 is going up. And by the way, you want to find parametric equations for the tangent line to that helix at the point 0, 1 pi over 2. Right? That's what it's saying here, at the point 0, 1 pi over 2. So what aren't they giving you here in example 3 that you need? In order to find the tangent line to this helix at a particular point, what do we need to know about the point in regards to this, in regards to our helix? Why is that point 0, 1 pi over 2? Why is it on the helix? They're saying that point is on the helix. Is there a reason why? How can we confirm that? That's right, Mary. We need to know what t equals. So for some value of t, the point 0, 1 pi over 2 is going to be on the helix. Oh, do we know the value of t? That's right, Logan. It's going to be pi over 2. Has to be pi over 2. No other choice. So, we just got to keep that in mind. Now, we're not going to use that information yet. First, we have to find the derivative vector. And so we do that here. We do that here. We find the derivative vector. And then it's mentioned. Now, we would have to find this out on our own, but it's not hard. I mean, it's not hard to find the t value. They make it easy. The parameter vector corresponding to that point is t equals pi over 2. And so the tangent vector there would be given, would have components -2, 0, 1. So now we have we have the parametric equations of the tangent line. Here are the parametric equations of the tangent line. So notice that the tangent line to the point 0, 1 pi over 2 would have to go in the direction of the tangent vector that has components -2, 0, 1. And notice that tangent vector, the components, the A, B, and C are going to be R -2, 0, and 1. In other words, if I maybe let me make it a little more clear here. Let me go to the whiteboard. So this is example 3 that we're looking at here. So hold on here. Let me just see. One moment, class. Right. So, okay. So the tangent line at the point 0, 1, pi over 2. Okay. And this is to the helix. Okay, that helix. The parametric equations are x equals negative 2t, y equals 1, and z equals pi over 2 plus 1t. But negative 2t, think of it as like 0 plus negative 2t. Think of 1 as 1 plus 0 times t. And then z is just pi over 2 plus 1/2 t. So do you see how the 0, the 1, and the 2, that's the point that the tangent line passes through. And then the components of the tangent line, which have negative 2, 0, and 1/2, well, those are just components of the derivative vector, which is negative 2. Hold on here. I might have, oh, I have an error here, don't I? This should equal 1. Sorry. Right. Negative 2, 0, and 1. So hold on. Let's take a little bit of this highlight off. Oh, come on. There we go. So in figure 3 here, there is let me make that a little bigger. There is the helix. Now notice it's not a circular helix, because the x is 2 cosine t and y is 1 times the sine of t. It's like a elliptical helix. But you see at the point 0, 1, pi over 2 on the graph there, when x is 0, y is 1, and z is pi over 2. Pi over 2, that's like 3.14 divided by 2, which is like about 1.5, right? But at that point, there's the red tangent line to that helix. There it is. Okay, are there any questions on that at all? Who's feeling good? Who's feeling good so far? Give me a thumbs up if you're feeling good. Excellent, excellent, excellent. Okay, well, let's go a little bit further here in the book. Let's go a little bit further. Excellent. Okay, so, of course, they mentioned that you can take the second derivative of a vector as well. If the first derivative of a position vector is velocity, what do you think the second derivative of the position vector would be? What would it represent? That's right, Alex. That's right, acceleration. Good, Yeva. Good, Logan. Okay, now there's something else too that we need to be, well, actually they kind of stole my thunder here, didn't they? They're saying right here in 10.4, we'll see how these can be interpreted as velocity. R prime and R double prime can be interpreted as velocity and acceleration vectors. So, okay, let's proceed on a little bit more here. Okay, now there are derivative rules for vectors, just like you have derivative rules for functions. You have derivative rules for vector functions. So, like for instance, the first rule here, well, it's very similar to the rule you've learned for derivative of a sum of two functions. The derivative of the sum of two functions is the sum of the derivatives. Well, the derivative of the sum of two vectors is the sum of the derivative vectors. And that makes sense because of the way the components are, right? You're working with components which are functions. Okay, so there are 6 different rules here, and you're going to need to know all of them. Okay, but as you know, on an exam, you'll have access to the ebook. But these are the 6 rules. Second rule says if you take the derivative of a constant times a vector, you can bring the constant out. Third rule says you can bring the function out, but not quite. Third rule says if you take the derivative of a function of t times a vector function, that's a function of t, it's going to be equal to, basically it's an application of the product rule. Now the fourth rule is also important. If you take the derivative of the dot product, it equals this rule here. If you take the derivative of a dot product. So this is actually a very nice little rule, and we're gonna, yeah, it looks, Logan, it looks like the product rule, doesn't it? It's with dots. So the derivative of u dot v is u prime dot v plus u dot v prime. Really, really quite amazing. And they prove this rule. They prove this rule below. Now, they do have derivative rules for the cross product as well. That's the 5th rule. But let's look at this this rule number 4. Let's look at the proof of it. So you can hold on here. I don't know why that's sticking up. So I have some things highlighted here. You let u and v have, the vector u has those components of f, those function components, f components. The vector v has g components, and you can write the dot product out this way, right? You can write it as, well, you know how to do the dot product of two vectors, and it's really the sum then of these products, these function products. So if you then want to do the derivative, just maybe, let's see, maybe I will highlight that. And let's see, I'd like to try to hold on. Let's see if we can have it all here. Yeah, so the derivative of the dot product, they show the steps here. IB says, why aren't rule 4 and 5 the same? I will, let me go into that. But look at the proof of this 4th rule. Hopefully it makes sense. The derivative of a sum is the sum of the derivatives. And then you're using the product rule. And then you're writing the summation of the sum as the sum of the summations. And that's going to give you then that'll prove the rule then. One moment here. One moment. No, rule four IB is dot product. You're taking the derivative of a dot product. You see in rule 4, there's like a dot there. But in rule 5, that cross is the cross product. See that times symbol isn't times in our class. It's the cross product. Excellent, excellent question. All right, all right. So one thing that is, I'm just gonna do this. Right, so like why would this fourth rule here? Why would this fourth rule, this one here, you know, where I mean it's actually an extremely important rule. And I'll show you why. It has to do with the fourth example in the textbook. So here, I'm going to just highlight this. If I can. Example 4 says, show that if you have a vector function and the length of the vector function is constant, then the derivative vector is orthogonal to RT for all of t. So an example of this, let me show you an example of this. What would an example of this be? Okay, so, let's say that R of t is equal, has components cosine of t and sine of t. And we're gonna let t go between 0 and 2 pi. Now we know that will trace out. Hold on. We know that that's going to trace out a space curve. That is going to be a circle. So a circle of radius 1. Okay. One moment. No, I don't want that. I want it in blue. I normally draw the vector functions. I draw the space curves in red. And the position vectors in blue. Okay, so here's R of t, tracing out this circle, which is our space curve C. Let's try to make everything look good. Now watch what I'm going to do here. Watch what I'm going to do. Well, all right, let me do something else. Let's say you wanted to find the length of this vector function. Okay, well, hold on. I don't want derivative here. I just want the length of the vector function. Well, we know how to find the length of a vector. We add the sum of the square. We square. I want to say it the right way. We square each component, add the components together, and then take the square root of the sum. So in this case, we're going to have the square root of cosine squared of t plus sine squared of t. Now, what is cosine squared plus sine squared of t equal to? T is an angle. Think of t. I mean, t is a parameter, but we can think of it like an angle too. Yeah, it equals 1. That's right, Alexander. So this is the square root of 1, which is 1. So this means that for this particular space curve, this is an example of a space curve where the length of the space curve vector, of the position vector, that's what I call this. I call r of t it's a vector function or a position vector because it gives coordinates, it gives positions on the space curve. This is an example where r of t is equal to a constant. It equals to a constant. Oh, and what is that constant? Well, the constant equals 1. So far, so good? All right. Well, now what I'm going to do is at this point here on that space curve, I'm just going to draw a tangent vector, okay? And I'm not even saying the tangent vector. I'm not worried about its accuracy. Let's just say, hey, okay, it's a tangent vector. Okay, it's a tangent vector. There it is. What can you tell me? What can you tell me about the angle here between the position vector r of t and the tangent vector? Good. Good, Yeva. Good, Alexander. It's 90 degrees. 90 degrees. Okay, 90 degrees. So this here is a right angle. Okay, that's 90 degrees. Okay. Let me pick another point. Let me pick another point here on the space curve. Let me pick one over here. Okay. Maybe right here. And let me draw another position vector. Over here. Okay, and I'll draw another tangent vector. What can you tell me about the angle between, okay, so this is r prime of t for some value of t. And of course, my, position vector. What can you tell me about the angle between between that derivative vector and position vector. And the 90 degrees again. That's right. Good. Good. So let me just trying to kind of emphasize. Could it be possible that then, I mean, this is an example, this planar curve, that's a circle of unit of length 1 in space. Okay, maybe I'll put I'll just put a 1 here, right? We know this is 1 here. -1, 1. I mean, we know what we're doing here. But could it be that for any vector function where the length of the vector function is a constant for all t, notice this is for all t, would it be the case then that the vector function for the space curve would be perpendicular to the derivative vector of the space curve? The answer is yes. That's right, Alexander. So when the length of your vector function is a constant, the vector function is perpendicular to the tangent vector. In other words, the position and tangent vectors are orthogonal when the position vector r of t has constant length. And this is a little simple example of that. Now, the proof of this relies on that fourth rule that you just learned here in section 10.2. And we're going to use that fourth rule. So let's look at it in the book. And let me just show you the details. So here we are. Let's prove that if the position vector, if its length is constant for all t, then r prime of t, the derivative vector, is perpendicular, or the tangent vector, r prime of t, is perpendicular to the position vector. So what they do is they do this. They say, okay, let's say, I mean, you wouldn't think probably to do this, but somebody thought of it, and here we are. You can take the dot product of the vector r with itself, and that would just equal the length of rt squared. Right? I mean, that's true. I mean, I don't particularly want to erase this picture yet, but if you have like a vector A that equals 1, 3, let's just say take something simple, and you take the dot product of A with itself, you're going to get 1 times 1 plus 3 times 3, and that equals 1 squared plus 3 squared. And that can be thought of as the square root of 1 squared plus 3 squared squared, which is the length of A squared. So if you take the dot product of a vector with itself, just see here, if you take a dot product of a vector with itself, that equals the length of the vector squared. So okay, that makes sense. That makes sense here. Now, what we have here is an equation. We have an equation then. The dot product of r with itself equals c squared. But we can take the derivative of both sides of this equation with respect to t. The derivative of a constant squared equals 0 on the right, and what's the derivative of the dot product on the left? Well, we're going to utilize the fourth rule, and absolutely amazing, really. And we get this result. But if 0 is equal to 2 times the dot product of r prime and r, well, that means the dot product of r prime and r, in other words, the dot product of the position vector with its tangent vector, has to equal 0. Has to. And therefore, we have the situation where r prime is orthogonal to r, or we could say the tangent vector is perpendicular to the position vector. But again, this is only in the case where the position vector has constant length for all t. And they actually, I showed you this for a circle geometrically, but they're talking about actually, you could do this for a sphere as well. If you think of a sphere, okay, draw the position vector from the origin to any point on the sphere. The tangent vector to that point on the sphere would be perpendicular to the position vector. Truly amazing. Are there any questions on this? Who's feeling good so far? I understand. Yep, I know what Yeva means. Alberto's good, Narina's good, Logan's good. Alexander, good. Okay, wonderful, wonderful. I always like to give everybody credit who answers. Arian, Brian, Abdullah, excellent. Alexander, good. Well, I will stop the recording here, and I want to give you a little time to work on section 10.2, a little classwork time to work on that assignment. So let me go ahead and stop the recording then. Excellent.